On July 1, 2025, under the pristine skies of northern Chile, an automated system designed to protect Earth from asteroid impacts sounded a silent alarm. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, flagged a faint point of light moving with unusual purpose against the starfield. At first, it was just another detection among hundreds, a routine blip on the screen that would typically be dismissed as a known object. This particular point of light, however, refused to conform to any known pattern. Its trajectory was peculiar, appearing to open outwards as if it had journeyed from the deepest chasms of space. Initial photometric readings measured it at a dim magnitude 19, making it nearly invisible even to highly sensitive instruments. It was a ghost in the cosmic dark, a whisper of motion that hinted at an extraordinary origin story. The astronomers at the Atlas survey, sensing something was amiss, relayed the data to the Minor Planet Center. The request was clear: other observatories needed to track this anomaly. Within hours, telescopes in Hawaii, Arizona, Spain, and South Africa turned their gaze toward the faint traveler. As data points trickled in from around the globe, they began to paint a picture that was both breathtaking and deeply mysterious. The numbers didn't lie. The orbit wasn't a closed ellipse, the familiar path of objects bound to our Sun. Instead, it was a wide, open hyperbola. This mathematical curve meant one thing: its orbital energy was too high for it to be a captive of our solar system. It was a visitor, a true wanderer that had journeyed from another star system, from an unknown corner of our galaxy. Official confirmation soon followed, sending ripples through the astronomical community. The object's excess velocity relative to the Sun was over 35 kilometers per second. This was the third interstellar object ever detected in human history, following the enigmatic Oumuamua in 2017 and Borisov in 2019. It was given a name that would soon echo in observatories worldwide: 3I Atlas, the third interstellar traveler, discovered by the very system designed to watch our skies. The confirmation of 3I Atlas as an interstellar object immediately focused all attention on its trajectory. Unlike comets born in our own Oort cloud, which loop back in predictable ellipses, its path was a one-way street. It had entered our solar system from the void, and once it completed its passage around the Sun, it would return to that same profound darkness, never to be seen again by human eyes. Models generated by NASA's Jet Propulsion Laboratory illustrated its gradual descent into our neighborhood. It first crossed the orbit of Neptune, then Uranus, entering a region once traveled by the Voyager probes. With each new observation, the faint light of the object revealed more evident activity. The distance to the Sun was shrinking rapidly, and the immense pressure of solar radiation was beginning to sculpt its nascent tail. The orbital path indicated that its perihelion, the point of closest approach to the Sun, would occur between October 29th and 30th, 2025. It would pass at a distance of 1.4 astronomical units, a path that would take it between the orbits of Earth and Mars. While enormous on a human scale, this proximity is close enough for the Sun to exert a brutal and transformative influence on any icy body. At this distance, surface temperatures can exceed 250 degrees Celsius, causing volatile ices that coat the nucleus to sublimate directly into gas. This process creates the coma, the diffuse, ghost-like cloud that gives a comet its ethereal appearance. For astronomers, this closed pass represented an unprecedented opportunity, a chance to watch an alien object awaken under the heat of a star it had never before encountered. The transit was to be monitored by a global consortium of observatories. From the European Southern Observatory in Chile to the Lowell Observatory in Arizona, every major telescope joined forces to measure its speed, brightness, and activity. But the early data was already showing irregular peaks in brightness, a chaotic flickering that no local comet had ever displayed. Something about this traveler was fundamentally different. From the moment of its discovery, observers noted that 3I Atlas presented a peculiar greenish hue. This coloration is a known signature in comets, typically indicating the presence of cyanogen and diatomic carbon molecules, which glow when excited by solar radiation. However, the brightness of this visitor was increasing in a worryingly erratic fashion, suggesting its surface was composed of materials far more volatile than those seen in our native comets. Scientists theorized that its outermost layer had been hardened by billions of years of exposure to cosmic radiation in the harsh interstellar environment. This process would have created a kind of crust rich in carbon and nickel, sealing more volatile compounds beneath. As observatories around the world began to release their own measurements, the picture of 3I Atlas became simultaneously clearer and more perplexing, a puzzle of alien chemistry. The initial spectra revealed unusual peaks in infrared emission, pointing to high proportions of carbon dioxide and carbon monoxide compared to water. In simpler terms, this was a comet that exhaled different gases. It was likely formed in a region of its home star system that was significantly colder than the birthplace of our own comets, a place where CO2 ice dominated over water ice. Every new piece of data reinforced the feeling of witnessing something that transcended the familiar. The nucleus, estimated to be around 2 kilometers in diameter, appeared to be rotating slowly, releasing intermittent jets of gas and dust. The variations in its brightness didn't follow expected patterns, indicating that either its active zones were scattered unevenly across its surface or its orientation was constantly shifting as it tumbled through space. For scientists, this was not merely a spectacle, it was a window into the formation of other planetary systems. Analyzing the molecules released by 3I Atlas could reveal the primordial ingredients of worlds orbiting other suns. If comets are time capsules from their place of origin, then 3I Atlas was an interstellar message sent from an impossible distance, and it was finally beginning to speak. As the data streamed in, one inevitable question dominated every discussion. Where exactly did 3I Atlas come from? Using reverse trajectory models, researchers at Harvard and Cambridge projected its path backward through thousands of years of galactic travel. The simulations were a complex dance of gravitational forces, an attempt to rewind time and trace the traveler back to its home. The results did not point to a specific star system, which would have been nearly impossible. However, they did provide an approximate direction of origin. The object appeared to have journeyed from the Sagittarius arm of the Milky Way, possibly from a region where young stars are still being born. This possibility excited the scientific community, as it meant the object could carry chemical traces from a stellar nursery. This traveler was moving at an astonishing speed, over 110,000 kilometers per hour relative to our Sun. There was no way to pinpoint its precise origin star. It could have been ejected from a system with a dying star, or perhaps from a young system where planets were just beginning to form, their chaotic orbits flinging smaller bodies out into the interstellar abyss. As it drew closer to the Sun, conditions began to change rapidly. Observatories noted that its coma, the cloud of gas and dust enveloping the nucleus, was growing much larger than expected for an object of its size. The comet was alive, reacting to the Sun's heat in a highly unusual way. Its intense green color indicated the presence of ionized molecules, likely activated by ultraviolet rays from our star. Every photon it received was a spark altering its surface, peeling back the layers of its long journey. The teams operating the James Webb Space Telescope began preparing for spectroscopic observations at perihelion. The goal was to detect the most volatile chemical components before the intense solar radiation completely disintegrated them, hoping to read the message before it vanished. As 3I Atlas continued its inbound journey, the Hubble Space Telescope conducted a series of follow-up images. These observations captured a rare phenomenon, a nearly symmetrical bipolar tail. This structure indicated that activity was erupting from both hemispheres of the nucleus simultaneously, a sign of widespread and intense outgassing. The object was not just waking up, it was bursting with energy from all sides. The scientific world began publishing preprints and provisional reports in journals like Nature Astronomy. The titles all shared the same sentiment: an exceptionally active interstellar visitor. It was a cautious description, but it reflected the general surprise within the community. No one had expected that such a relatively small object could display such dramatic signs of activity while still so far from the Sun. But the most critical moment was still to come. On October 29, 2025, 3I Atlas would reach its point of maximum exposure to solar energy. The sensors of the Solar and Heliospheric Observatory, or SOHO, had already detected a slight fluctuation in dust and gas in its vicinity, a clear signal that the comet was reacting strongly to the bath of radiation it was now entering. Astronomers knew that something unusual could happen, but no one could anticipate the sheer magnitude of what was about to unfold. At that moment, 3 Atlas became the most intensely observed object in the solar system. Thousands watched live feeds from professional and amateur observatories, awaiting the moment the comet would cross the imaginary line marking its perihelion. The instruments began to register a sudden surge in brightness that far exceeded model predictions. The core of 3I Atlas seemed to be responding to the Sun in a way never seen before. This was the signal that marked the beginning of a new stage in its journey, a phase that would leave science facing a series of unanswered questions about the nature of this interstellar traveler. In the months leading up to its solar encounter, 3I Atlas began to defy all expectations. Between August and October of 2025, its brightness increased by a factor of 8. This anomalous surge was far greater than what would be expected for a comet at its distance. Spectroscopic measurements revealed the cause. The comet was venting extremely high levels of CO2 and carbon monoxide, but very little water vapor. This distinct chemical signature confirmed that 3I Atlas was fundamentally different from the comets born in our own solar system, where water is the dominant component. Its birthplace must have been an extremely cold region, perhaps on the frigid outskirts of a distant planetary system where carbon dioxide remains frozen for millennia. It was a relic from a place far colder than our own solar backyard. The James Webb Space Telescope, with its unparalleled infrared sensitivity, became a crucial tool in this investigation. During September, its MIRI instrument registered the comet's thermal signature as it crossed the 2 astronomical unit mark. The emission curves revealed that the surface of 3I Atlas was covered by a crust hardened by cosmic radiation, so dense that heat could barely penetrate more than a few centimeters. This outer layer of carbon and silicates acted as a protective shield, but it was also accumulating immense internal tension. Scientists suspected that as it reached perihelion, thermal expansion could fracture this crust, releasing violent jets of trapped gas from within. The comet was effectively a pressurized container, sealed for eons, and now the Sun was turning up the heat, threatening to break the seal. Meanwhile, amateur observers on Earth began tracking its movements with medium-sized telescopes. In the early weeks of October, the comet appeared faint at magnitude 13, visible only through long photographic exposures. However, calculations predicted it would reach magnitude 8 near perihelion, bright enough to be seen by experienced astronomers in dark sky locations, a faint but determined ghost in the night. The irregular surges in brightness that puzzled astronomers soon resolved into a discernible pattern. By combining data from telescopes on 3 continents, a global monitoring campaign revealed that the brightness variability followed a cycle of approximately 12 hours. This rhythm was consistent with the rotation period of the comet's nucleus, a discovery that provided the first major clue to its strange behavior. At each peak of brightness, the spectrum showed a temporary spike in CO2 emission lines. It was as if the comet was exhaling a plume of gas every time a specific active zone on its surface rotated to face the Sun. This was the first direct evidence of a periodic source of activity on an interstellar object, a rhythmic pulse beating from the heart of an alien world. At the ESA's Planetary Study Center, analysts attempted to model this phenomenon. They used thermodynamic simulations based on the conductivity of ice and the expansion of gases trapped beneath a porous crust. The results indicated that small pockets of CO2 could build up pressure until the surface fractured, expelling material at speeds exceeding 150 meters per second, creating micro-explosions. Each of these small eruptions would release thousands of tons of gas and dust, enough to significantly increase the comet's overall brightness. These events explain the observed peaks and the peculiar jet activity. It appeared 3I Atlas was not just a solid body, but a dynamic engine, powered by the Sun and its own ancient, trapped volatiles, firing off jets with the regularity of a cosmic clock. This periodic activity also explained an intriguing detail revealed in photographic records: the comet's tail. Instead of pointing directly away from the Sun, it was slightly curved to one side, forming an unusual angle. This discrepancy suggested a non-thermal component in the material ejection, likely a directed jet influenced by the nucleus's rotation, creating a visible, oscillating pattern in long-exposure images. The discovery of the comet's rhythmic pulses transformed the observation campaign into a global vigil. The scientific community mobilized its resources to watch 3I Atlas continuously, passing the observational torch from one continent to the next as the Earth rotated. The goal was to capture every fluctuation, every subtle change in its behavior as it made its final approach toward the Sun. In mid-October, space-based telescopes registered a second event, even more intense than the first. The James Webb captured a sudden infrared flare that lasted less than 6 hours, accompanied by a sharp spike in visual brightness. The amount of energy released was equivalent to the evaporation of about 10 million kilograms of CO2 ice, a sudden and massive release of gas from the comet's surface. This phenomenon was unofficially dubbed the Atlas Pulse. From that point on, every variation in brightness was compared to this reference event. Scientists highlighted the importance of these pulses for understanding comets from other planetary systems. If 3I Atlas formed in an environment rich in solid carbon dioxide, it implied its home star might have had an extremely cold outer region, offering clues about its planetary architecture. This increasing brightness also posed a technical challenge. The coma became so extensive and bright that traditional photometric models were no longer accurate. Astronomers had to use specialized filters to separate the light of the nucleus from the glare of the surrounding dust. Hubble images revealed the coma had stretched to over 80,000 kilometers in diameter, double the expected size, a vast glowing shroud. Meanwhile, instruments on SOHO and the solar orbiter were monitoring the region around the Sun. Both detected slight increases in dust and gas coming from the direction of 3I Atlas, a direct effect of solar radiation striking an object that had never before experienced such intense heat. This alien body was beginning to shed pieces of itself into our solar system, seeding our space with foreign material. As the days of October counted down, the Sun's influence on 3I Atlas grew exponentially more powerful. Deeper numerical models showed how the Sun's magnetic field was interacting with the comet's tail. The ionized particles of CO and C2 were reacting to the solar wind, forming undulating and variable structures. Astronomers compared it to a ribbon of light that responded to every blast of plasma emanating from our star. This magnetic interaction indirectly revealed details about both the Sun's field and the electrical properties of the gas ejected by the comet. As the data confirmed, 3I Atlas was not just an interstellar traveler, it was a natural laboratory. Its unique trajectory allowed for the study of how matter from another star system behaves, when subjected to the environment of our own star. Within every emission of gas, in every change of brightness, information was hidden about its primordial composition, about the chemical processes that occur in distant worlds. The day of reckoning, October 29th, finally arrived. From different points on the planet, observatories awaited the moment of perihelion. The tension in control rooms around the world was palpable. Any variation could signal a massive release of internal energy. James Webb aimed its instruments toward the region where the comet was hidden by solar glare, while Hubble prepared observations in ultraviolet wavelengths to detect potential fragments. When the first data packets began to arrive, monitors showed a sudden, extreme spike in brightness. 3I Atlas was reflecting more light than anticipated and exhibiting an accelerated expansion of its coma. This was the moment everyone was waiting for. Preliminary analysis indicated that the nucleus's surface had partially fractured, allowing jets of gas and dust to escape in multiple directions. One of these jets, according to the measurements, was behaving in a way that seemed to defy the known laws of cometary physics. It was aimed not away from the Sun, but directly toward it, challenging everything astronomers thought they knew. At 14:23 Universal Time, the instruments of the solar orbiter registered a sudden burst of particles erupting from 3I Atlas. Shortly after, observatories on Earth confirmed that the comet had released an enormous plume of gas and dust. This brilliant cloud, however, was not pointing away from the Sun as expected. It was aimed directly at the star, a behavior that was utterly contrary to known physics. Unlike comets in our solar system, whose tails are always pushed away by the pressure of the solar wind, 3I Atlas displayed a stunningly counterintuitive action. Its main jet appeared to be heading directly into the source of the radiation that was causing it. Scientists analyzed the data again and again, certain it had to be a trick of perspective or an optical illusion. But orbital calculations and jet vectors confirmed the impossible. The ejection was real, and it was almost perfectly aligned with the Sun. The phenomenon was simultaneously detected by the Stereo A telescope and Hubble, which captured images showing a thin column of material extending toward the inner solar system. This was something new, something that had never been witnessed before. Spectra revealed that the jet was primarily composed of carbon dioxide and fragments of amorphous carbon-rich dust, with no signs of water ice. This was unprecedented. The Sun's heat had penetrated deep enough to sublimate the most volatile compounds, but had somehow failed to destroy the nucleus. 3I Atlas was responding to the Sun in a way that traditional models simply could not reproduce. Researchers at NASA compared the sequence with historical records of sun-grazing comets like Lovejoy and Ison. None had ever displayed a jet directed toward the star with such intensity. The phenomenon was quickly given an informal name, the active antitail. But unlike a typical antitail, which is an optical illusion, this was a real flow of particles moving against the current of the solar wind. The James Webb Space Telescope, observing from its stable position at Lagrange Point 2, barely managed to capture the last infrared vestiges of the event before the Sun's intense glare saturated its sensors. Even so, the data was sufficient to estimate the temperature of the ejected material at around 43 degrees Celsius, significantly colder than the comet's surface, a crucial clue. This temperature difference suggested that the gas was rapidly expanding from an internal cavity, a kind of cosmic exhalation that released its contents into space. Meanwhile, the Solar Orbiter probe registered a temporary increase in the density of the solar wind in that region, accompanied by a slight magnetic disturbance. The implication was extraordinary. Material from the comet had directly interacted with solar plasma. For the first time, an object from another star system was altering, however minimally, the immediate environment of our Sun. In analytical labs, astrophysicists tried to reconstruct the physical process behind this strange ejection. The most widely accepted hypothesis pointed to a phenomenon of internal overpressure built up over millions of years of travel through the absolute cold of interstellar space. The comet had accumulated gases in pores and fissures under a hardened outer layer. When the sun's heat finally reached these trapped pockets, the rapid expansion of CO2 and carbon monoxide ruptured the surface like a pressure valve. The result was a sudden, directional ejection, its aim guided by the rotation of the nucleus and the specific location of the fissure. The Palmer Observatory recorded that the comet's apparent magnitude increased by nearly a full point in just 3 hours. Images showed a much denser coma and a filamentous structure within the jet zone, with particles extending for more than 50,000 kilometers. The flow appeared so stable that astronomers compared it to a geyser of ice and gas being expelled into the vacuum. The impossible plume was not just a visual spectacle, it was an invaluable source of scientific information. The particles released in the jet reflected the deep composition of the comet's core, material that had never before been exposed to the vacuum of space. The spectra showed traces of complex organic compounds, including formaldehyde and hydrogen cyanide, molecules essential for prebiotic chemistry. Their detection was consistent with what has been observed in other comets, but their proportions were different, indicating a unique chemical history. These signals confirmed that 3I Atlas came from a stellar environment where the formation of organic molecules occurred under conditions of extreme cold and radiation, a different path to life's building blocks. Scientists at ESA published a preliminary report detailing the event's characteristics. They estimated that the total mass ejected was equivalent to over 40 million kilograms in a period of less than a day. Although this amount represented only a tiny fraction of the comet's total mass, it was enough to dramatically modify its appearance and produce the spectacular plume observed from Earth. The dynamics of the jet stream, according to calculations, would have also slightly altered its rotation, accelerating it by about 3%. The interaction with the solar wind generated an additional luminous effect. As charged particles from the sun struck the expelled gas, they produced ionization discharges that made the plume glow in ultraviolet wavelengths, a dance between interstellar matter and stellar atmosphere. For scientists at the Institute of Astrophysics of Andalusia, this encounter offered a unique opportunity to study the boundary between cometary dust and solar plasma. As the comet passed behind the sun from Earth's perspective, visual observations paused. However, instruments on Solar Orbiter and the stereo satellites continued to detect the cloud of material moving toward the solar corona, a ghost still haunting our star. After its dramatic encounter with the sun, the world held its breath. When 3I Atlas re-emerged on the other side in early November, telescopes confirmed it had survived perihelion. Its nucleus remained intact, although it now presented a more irregular shape and an extensive tail stretching over 100,000 kilometers. The extreme brightness had faded, but the comet had endured. What most astonished astronomers was the resilience of its core. Despite the extreme thermal stresses, it had not disintegrated or fragmented. This suggested a structure far more compact than expected, perhaps cemented together by metallic materials or solid silicates. Follow-up analysis from Hubble and Webb confirmed that the nucleus maintained a higher density than that of typical solar system comets. This finding matched observations of its trajectory. There were no signs of significant mass loss that would indicate a major structural failure. Its behavior had been violent, yes, but also controlled. 3I Atlas seemed to have relieved its internal pressure without compromising its structural stability, a feat that defied all previous experience with comets that venture so close to a star. In scientific circles, the event was described as a natural experiment in extreme physics. No terrestrial laboratory could ever reproduce the conditions of this encounter between interstellar matter and solar energy. For the first time, scientists had direct evidence of how a body formed under another star responded to the crucible of our own. And the answer was one of surprising strength. The data captured during the outburst would fuel years of research into the thermodynamics of comets. The jet pointed toward the Sun was the clearest proof yet that 3I Atlas did not behave like a conventional comet. Its composition, its structure, and its method of releasing energy revealed a new class of object, a messenger from deep space that briefly allowed us to witness an impossible dialogue between worlds. With 3I Atlas in a prime viewing position, the James Webb Space Telescope activated its real-time observation mode, reserved for unrepeatable cosmic events. Its spectrometers, NIRSpec and MIRI, captured the comet's thermal radiation during its peak activity phase. The initial data revealed a spectrum dominated by bands of carbon dioxide, carbon monoxide, and simple organic molecules like methane and hydrogen cyanide. The almost total absence of water was the first major surprise. 3I Atlas was not a typical comet from our Oort cloud, but an object formed in a region so cold that water ice could never have been abundant. The spectrum also presented an unusual absorption pattern near 3 micrometers, an indication that the surface was covered by complex carbonaceous materials, the building blocks of more complex chemistry. The team compared these signals with those from other comets observed by Webb, like Hartley 2 and Tempel 1. They found that the signatures of 3I Atlas were more consistent with the remnants of young protoplanetary disks than with mature comets from our solar system. In other words, 3I Atlas appeared to have originated in a newborn star-forming zone where material had not yet undergone extensive processing. From the thermal data, scientists calculated the surface temperature of the nucleus to be around 103 degrees Celsius. This was surprisingly low considering the intensity of the solar radiation it received. It meant the outer layer of the comet acted as a highly efficient insulator, keeping the interior frozen while releasing gases through localized fractures. The hardened crust was its salvation. Webb's mid-infrared images showed an asymmetrical glow that coincided with the position of the jet aimed at the Sun. The energy emitted in that region was 3 times higher than on the rest of the surface, confirming localized activity. The telescope also detected solid particles a few microns in diameter, likely silicate grains expelled with the gas, providing a complete inventory of its alien composition. One of the most valuable results from the James Webb analysis was the detection of an anomalous ratio of carbon and oxygen isotopes. The telescope registered a higher ratio of carbon-13 to carbon-12 than expected, something only observed in galactic regions where star formation has been intense for long periods. This was the chemical fingerprint astronomers had been hoping for, a clue to its birthplace. This allowed researchers to trace the possible origin of 3I Atlas to an older region of the Milky Way, perhaps some 300 light-years away in the Sagittarius Arm. For the first time, an interstellar object brought with it an isotopic record that could be used to backtrack to its home region. It was a chemical postcard from a distant and ancient part of our galaxy. As 3I Atlas began to move away from the Sun, its infrared emissions slowly decreased, but the spectral patterns remained stable. There were no signs of catastrophic fragmentation or mass loss. The activity seemed controlled, as if the nucleus was periodically releasing pressure. This stability contrasted sharply with the explosive behavior of solar comets like ISON, which disintegrated on its first pass. Experts at the Max Planck Institute for Astronomy analyzed the temperature distribution on the nucleus and found a difference of up to 40 degrees Celsius between its hemispheres. This thermal inequality generated stresses that explained the directional gas leaks. Each jet acted as a natural propellant, which they deduced had slightly accelerated the comet's rotation after its perihelion passage. What do you think this strange object's resilience tells us about planet formation elsewhere in the galaxy? Share your theories in the comments. Hubble, operating in ultraviolet wavelengths, complemented Webb's observations by tracking molecules excited by solar radiation. Comparing the two datasets allowed for the construction of a three-dimensional model of the gas behavior around the nucleus. It showed material being ejected in pulses, confirming that the active zones were periodically turning on and off as the comet rotated. The first images sent back by Webb, Hubble, and the solar orbiter prompted an immediate reaction at the control centers of NASA and ESA. They knew the behavior of 3I Atlas was an unprecedented phenomenon and a scientific opportunity that could not be missed. Within hours, both organizations coordinated an international network of observatories to monitor every change in the object's brightness, trajectory, and composition. The response was swift but cautious. Public statements emphasized the need to analyze the data thoroughly before drawing any premature conclusions. At the Jet Propulsion Laboratory, orbital dynamics experts confirmed that despite the material ejection, the comet's trajectory had not deviated significantly. It was still on a hyperbolic curve that would carry it out of the solar system, posing no risk to Earth. On October 31st, NASA published a preliminary report titled Interstellar Visitor. 3I Atlas shows unprecedented activity at perihelion. The document precisely described the data, confirming the object's interstellar nature and its extraordinary resistance to solar heat. The agency highlighted the unexpected brightness surge, the CO2-rich composition, and the absence of water, all pointing to an alien origin. Meanwhile, at ESA's Space Operations Center in Germany, teams from Solar Orbiter and the Gaia Observatory convened. Their goal was to compare the exact position of 3I Atlas with models of the Sun's magnetic field. The data showed a small disturbance in the solar wind coinciding with the comet's ejection, a faint but tantalizing signal that a piece of this visitor had mingled with our Sun's plasma. On November 2nd, ESA issued a joint statement with NASA describing 3I Atlas as a window into the chemical origins of other star systems. The note detailed that both agencies would share all their data in an open-access database for researchers worldwide. This rapid global collaboration was a testament to the significance of the event, as the scientific community raced to document the visitor before it vanished. In Houston, the Johnson Space Center opened a temporary room dedicated exclusively to the analysis of 3I Atlas. Scientists there compared the detected molecular ratios with those from meteorites and dust samples collected by missions like Stardust and Rosetta. The results were intriguing. The carbon and oxygen ratios partially matched a rare type of carbonaceous chondrite, reinforcing the idea of an origin in a distant planetary system. The James Webb continued to deliver data as teams on the ground processed the spectra. NASA decided to release some of the observations on its public portal, and the images quickly went viral. They showed a brilliant head surrounded by a blue-green coma and a dual tail stretching for over 100,000 kilometers. The popular interest soared to levels comparable to major planetary missions. The agency leveraged this attention to launch educational campaigns, explaining the difference between scientific observation and speculation. They organized live streams with astronomers answering public questions about how to interpret a spectrum or why a comet's tail behaves the way it does. The goal was to transform general curiosity into learning, a way to use the media spotlight to disseminate science. In Europe, ESA organized a special conference where Spanish astrophysicist Javier Martínez Santos presented the first results from the Solar Orbiter probe. He detailed a series of variations in solar wind density attributable to the passage of the 3I Atlas plume. His presentation concluded with a sentence that stunned the audience. For the first time, we have seen how matter from another star system can directly interact with the solar environment. This news spread through specialized media in a matter of hours. The scientific interest then turned into a race to record every detail before the comet disappeared from view. Observatories on every continent coordinated a continuous observation schedule, ensuring that as the Earth turned, another telescope was always ready to take over, keeping a constant watch on the departing alien. Just as the scientific community began to process the perihelion event, 3I Atlas delivered another profound shock. On November 3, 2025, with the comet already receding from the Sun, telescopes detected an abrupt variation in its brightness. It surged by nearly 1.5 magnitudes in less than 2 hours. This was not a simple temperature fluctuation, it was a genuine outburst, a new episode of activity that no one expected. Scientists immediately called it the second pulse, although they would soon understand it was something different, something far more powerful than the gaseous pulses seen before. The first images showed a rapid expansion of the coma, accompanied by a secondary cloud of dust extending in the opposite direction of the main tail. The comet's core appeared intact, but its brightness had peaked in a matter of minutes. Observatories in the southern hemisphere, including those in Chile, managed to capture the entire sequence. The photographs showed a kind of halo around the nucleus, as if a layer of its surface had suddenly detached. Spectral emissions of carbon dioxide spiked by 40%, confirming a massive delayed release of gas. The event was baffling because it happened as the comet was moving away and cooling down. Researchers at the Planetary Science Institute in Arizona proposed a tentative explanation. According to their models, the accumulation of thermal stress during perihelion had generated internal fractures that took days to propagate. When these cracks reached deep pockets of trapped gas, the released pressure caused a delayed eruption. It was a thermal echo from its encounter with the Sun, a kind of final shuddering breath. The James Webb, still in its automated tracking mode, detected the change almost immediately. Its infrared sensors registered a sudden spike in radiation from hot dust. Preliminary analysis indicated that the local temperature of the coma had soared to 27 degrees Celsius, much hotter than it had been at perihelion. Something had fundamentally altered the comet's thermal structure, as if a piece of its surface had simply collapsed. The post-perihelion outburst from 3I Atlas was powerful enough to be felt across the inner solar system. The Solar Orbiter probe detected a small disturbance in the solar wind, with a high density of particles coming from the comet's direction. The ejection had been sufficiently energetic to affect the immediate environment of interplanetary space, releasing a cloud of material visible from millions of kilometers away. Over the next few hours, telescopes in the northern hemisphere began to record the phenomenon's evolution. Unlike previous outbursts, this one did not dissipate quickly. The dust cloud remained visible for days, expanding as the comet continued on its trajectory. Dynamic models from Cambridge University showed that the expansion velocity exceeded 250 meters per second, a speed that could only be explained by a partial structural collapse. Yet remarkably, the main nucleus did not break apart. Hubble observations confirmed it was still a single body, albeit slightly more irregular. The comet's brightness began to fade again, but the secondary cloud persisted, leaving behind a luminous trail that was visible for over a week. In astronomical forums, observers compared the event to a controlled mini-explosion, a demonstration of the comet's ability to release energy without self-destructing. The most stunning finding came from the ultraviolet spectrum. For the first time, scientists detected clear signs of the fragmentation of complex organic compounds in space. The characteristic bands of formaldehyde and hydrogen cyanide showed a sharp decline, a signal that these molecules had been destroyed by the energy released in the blast. The explosion was not just physical, but chemical. In the minutes following the event, the comet emitted a greenish glow more intense than normal, visible even to optical cameras. This light came from the ionization of diatomic carbon in the coma, activated as solar light interacted with the freshly released gas. In simple terms, the comet had lit up its own aurora, a plasma display visible across the vacuum, another unprecedented behavior. The news of a second, even more powerful outburst left the scientific community in a state of quiet admiration. In the first few minutes, teams at Webb and Hubble thought a sensor had failed. The light curves shot up so abruptly that some monitoring algorithms dismissed the readings as errors. But when images from Chile, Hawaii, and the Canary Islands all confirmed the same pattern, the reality was undeniable. At the Jet Propulsion Laboratory, the operations room buzzed with messages as scientists worldwide exchanged real-time data. Cometary dynamics experts reviewed trajectory vectors, astrophysicists compared the brightness intensity with thermal models, and planetary chemists analyzed the spectral lines. The scene was reminiscent of the Apollo missions: illuminated screens, tense voices, and a mixture of excitement and profound perplexity. No one expected an interstellar object to exhibit such intense activity after passing the most dangerous point of its journey. Initial hypotheses emerged within hours. Some thought the explosion was due to an internal fracture caused by the temperature shift between hemispheres. Others proposed that the comet contained reactive compounds, like frozen peroxides, that had suddenly decomposed. Yet no single explanation could justify the event's magnitude. At ESA headquarters, Solar Orbiter mission engineers convened an emergency meeting. Their plasma sensors had detected a pulse of particles that coincided with the optical outburst, tangible proof of the comet's interaction with the solar wind. It was the first time an interstellar object had produced a measurable disturbance in the heliosphere, a small wave propagating through the Sun's magnetic field. The Planetary Science Institute in Tucson published a report claiming the outburst was the first documented case of delayed activity in an interstellar comet. They interpreted it as the nucleus having accumulated heat in its inner layers during perihelion. Days later, this heat finally reached trapped gas pockets, triggering a delayed eruption. The term post-perihelion outburst quickly became the official label for the event. On November the 5th, just 2 days after the second outburst, NASA held a press conference. Before a packed room of journalists, program directors calmly explained the confirmed facts. "What we have witnessed is a natural but extraordinarily powerful process," one director stated. 3I Atlas has demonstrated a form of activity we have not observed in any other interstellar body. There is nothing artificial, but rather physics we are just beginning to understand. That sentence set the tone for all subsequent media coverage. Wonder, but without speculation. Theoretical astronomers then began a race against time to reproduce the event through simulations. A team at the University of Maryland used three-dimensional heat transfer models, inputting a highly refractory outer layer with low thermal conductivity and a more porous core, rich in frozen CO2. The result matched the observations almost exactly. After receiving an intense dose of radiation, heat penetrated slowly to an internal cavity, building pressure until it was suddenly released. The simulation showed a gas ejection directed toward the illuminated hemisphere, just as the real images had shown. The model provided a powerful, physically grounded explanation for the comet's strange delayed reaction. One of the most debated points was the structural stability of the nucleus. If 3I Atlas could release so much energy without fragmenting, its interior had to be far more resilient than expected. Some suggested the cohesion came from metallic bonds or mineral compounds acting as cement. Others pointed to the possibility that the comet had lost much of its original porosity during its long interstellar journey, becoming compacted over time. Observational astronomers, meanwhile, continued to gather data. The Very Large Telescope recorded the coma's evolution after the explosion. Analysis showed that although the gas density decreased rapidly, the dust remained dispersed in a filamentary structure that reflected sunlight with a bluish tint. This coloration came from extremely small particles, the size of smoke grains, formed by the rapid condensation of the emitted material. With the final fading of 3I Atlas, scientists began to place it in context, comparing it to the two interstellar visitors that came before, Oumuamua and 2I Borisov. Each of these three bodies had challenged the expectations of its time. Together they outlined a new field of study, a galactic census of the objects that wander between the stars, each one a unique messenger. The first visitor, Oumuamua, detected in 2017, was a fleeting mystery. Unlike 3I Atlas, it showed no visible coma or tail. Its brightness varied irregularly, suggesting an elongated shape or a highly reflective surface. It was moving at over 87 kilometers per second and left the solar system before telescopes could get a high-resolution look. Its lack of cometary activity led many to believe it was a rocky or metallic fragment. 2 years later, 2I Borisov appeared. Discovered by an amateur astronomer, it displayed a classic, clear cometary tail. It contained large amounts of water and hydrogen cyanide, indicating a composition similar to comets from our own Oort cloud. However, Borisov partially fragmented as it approached the Sun, demonstrating a fragile and porous structure, a loosely packed ball of ice and dust. Then came 3I Atlas. It combined characteristics of both its predecessors, the hyperbolic trajectory of the first and the cometary activity of the second, but with an unprecedented structural resilience. Researchers soon realized that 3I Atlas represented a new class of object, denser, more complex, and with a chemical composition different from anything observed before, a true hybrid of comet and asteroid. While Oumuamua revealed that solid, inert fragments can travel between star systems, and Borisov demonstrated that familiar-looking comets can too, 3I Atlas showed that these travelers can be far more active and stable than imagined. It proved they are capable of surviving intense solar radiation and responding with controlled, powerful dynamics. In a way, each object expanded the very definition of interstellar matter. The velocities of the three interstellar visitors told their own stories. Oumuamua entered at 26 kilometers per second relative to the Sun, Borisov at 32, and 3I Atlas at 35. This progression suggested they came from distinct galactic regions with independent histories. Models from the Harvard-Smithsonian Center indicated 3I Atlas likely originated in an area of high stellar density, perhaps an open cluster where gravitational interactions frequently eject smaller bodies. Their internal structures were also starkly different. Oumuamua, with no cometary activity, was likely a compact fragment of rock or metal. Borisov, fragile and volatile, was more akin to our own Oort cloud comets. 3I Atlas, however, occupied a middle ground, dense enough to withstand the heat, but still capable of releasing gas and dust. It was a natural hybrid, a bridge between interstellar asteroids and active comets. The contrast in their chemical makeup was equally revealing. Oumuamua presented a flat, featureless spectrum. Borisov contained water and cyanide in familiar proportions, but 3I Atlas exhibited an absolute dominance of carbon dioxide and carbon monoxide. This radical difference implied that each one formed under different chemical conditions, reflecting the diverse environments of planetary systems across the galaxy. Researchers proposed a unifying model. Interstellar objects are the natural product of the evolution of young star systems. During the formation of giant planets, many smaller bodies are ejected and wander the galaxy. Some lose their volatiles and become rocky fragments like Oumuamua. Others, like Borisov and Atlas, preserve their ice and gas, becoming chemical messengers from their home stars. The timing of their detections also fueled the hypothesis that the transit of interstellar visitors is far more frequent than previously thought. Galactic dynamics studies indicate that on average an object the size of Oumuamua crosses the inner solar system every year, though most pass undetected. 3i Atlas confirmed that with new observation technologies, these visitors are no longer rarities, but a common phenomenon. From the earliest human records, the Sun has been a symbol of both life and destruction. For astronomers, however, our star is also a laboratory. Its light, its wind, and its magnetism become tools that reveal the nature of objects venturing into its domain. In the case of 3i Atlas, this interaction was fundamental to understanding its alien nature. As the comet approached within 1.4 astronomical units, solar radiation began to alter its molecular structure. Each photon striking its surface triggered a chemical reaction. Spectra from the James Webb showed a phenomenon called photodissociation. Complex molecules on the comet's surface broke apart under the ultraviolet light, releasing individual atoms of carbon, oxygen, and nitrogen, which created its signature green glow. The solar wind, a continuous flow of charged particles, played an even more dramatic role. As protons from the wind collided with the gases in the coma, they created microscopic shock waves. The solar orbiter's instruments registered these disturbances in the local magnetic field, showing that the comet's atmosphere had become a small shield resisting the solar onslaught. It was a silent duel between interstellar matter and stellar energy. Plasma dynamics models from ESA showed that the solar wind not only pushed the tail of 3i Atlas, but also shaped its internal structure. The charged particles induced electrical currents in the gas cloud, causing the tail to bifurcate into two distinct components: a dust tail, formed by neutral particles reflecting sunlight, and an ion tail composed of excited gas that followed the Sun's magnetic field lines. This phenomenon allowed scientists to study how the solar wind varies with distance. By analyzing the orientation of the comet's tail, they could measure the local plasma speed with a precision previously achievable only with direct probes. In a sense, the comet itself served as a natural diagnostic tool, mapping the invisible forces that shape our solar system from within. The Sun's role was not limited to the comet's external environment. It also transformed its interior. As energy slowly penetrated the hardened crust, the heat generated stresses that caused the periodic release of gas. Each pulse of activity observed in the weeks leading up to perihelion was a direct response to the increasing solar radiation. Without the Sun, 3i Atlas would have remained a dormant, invisible fragment. In a way, the Sun acted as a cosmic catalyst. It did not destroy the visitor, but forced it to reveal its structure, chemistry, and resilience. The heat was strong enough to generate activity, but not intense enough to disintegrate it, a perfectly calibrated dance of energy. It was a dual reflection. The comet taught us about interstellar matter, and in doing so, it offered new information about our own star. On a chemical level, the Sun served as a laboratory for photonic reactions. The ultraviolet radiation broke molecular bonds and generated free radicals that recombined to form new compounds. Hubble's spectra detected traces of formaldehyde and acetylene that were not present before perihelion. The Sun had effectively cooked the comet's surface, altering its chemistry and leaving a new spectral signature for astronomers to track. This encounter also offered lessons on the physics of sublimation. In terrestrial labs, scientists simulated the perihelion conditions using vacuum chambers and UV lamps. They found that mixtures of CO2 and CO, when subjected to rapid temperature changes, could generate directional jets just like those observed on 3i Atlas. The Sun, with its constant energy flux, acted as the trigger for these natural micro-explosions. For solar astrophysicists, the visit was also an unexpected opportunity to study how comets contribute to interplanetary dust. The material ejected toward the Sun was temporarily integrated into the zodiacal dust flow. By observing its dispersion, researchers calculated that a tiny fraction of this alien dust will remain orbiting near the Sun for decades, a microscopic trail left behind by the interstellar visitor. After perihelion, as 3I Atlas began its slow retreat from the Sun, its story entered a new, quieter phase. Many assumed the spectacle was over, but telescopes continued to detect signals demonstrating that the visitor still had more to say. The cooling down phase is just as important as the moment of peak activity, as it defines the physical and chemical consequences of the stellar encounter. As the comet moved beyond 1.6 astronomical units, the intensity of solar radiation diminished and the gas flow gradually reduced. The coma began to contract. What was surprising, however, was that even with less energy, the comet continued to exhibit faint, intermittent peaks of brightness. These were the last active vents on its surface, areas that continued to release gas trapped in deep fissures. The James Webb continued to observe, detecting a drop in surface temperature to 153 degrees Celsius. Yet its infrared sensors registered a curious phenomenon. The comet's interior still retained residual heat from perihelion. Simulations showed this heat would take weeks to dissipate completely, explaining the prolonged activity. 3I Atlas was cooling slowly from the inside out, like a stone still holding the fire of its last solar contact. This cooling process had visible effects on its appearance. The main tail began to extend, reaching over 300,000 kilometers, while a second, thinner tail of fine dust slowly separated from the main axis. The coma's color also shifted from the intense green of perihelion to a pale bluish hue, a result of decreasing ionized cyanogen. This color change was precisely documented by Hubble. The composition of the outgassing material also changed. Carbon dioxide remained the primary component, but traces of methane, ethane, and ammonia began to appear as the more volatile gases were depleted. This phenomenon allowed for the reconstruction of a kind of chemical stratigraphy of the comet. Each phase of its journey had revealed a distinct layer of its interior, a geological survey from afar. Researchers comparing observations of 3I Atlas with models of cometary evolution made a startling discovery. The object had lost less than 3% of its total mass during its passage through the solar system. This was an astonishingly low number considering the intensity of its encounter. Local comets like Ison disintegrated completely, but 3I Atlas had suffered little more than superficial erosion. This was the definitive confirmation of its compact and dense nature, a core capable of withstanding extreme thermal forces. The comet's rotation had also changed after perihelion. Photometric observations showed its rotation period had shortened from 12 to 10.8 hours. This acceleration was a direct consequence of the gas ejections, with each jet acting as a small propellant transferring angular momentum to the body. The orbital dynamics team at JPL calculated the object's new trajectory using post-perihelion measurements. The result confirmed 3I Atlas was still on a hyperbolic orbit with an escape velocity of 35 kilometers per second. It would never return. Once its journey through the inner solar system was complete, it would be lost again to interstellar space, heading toward the void between the stars. But before its final farewell, the comet left one last gift. In December 2025, the solar orbiter detected a diffuse cloud of particles along the path it had traveled weeks earlier. This cloud was composed of dust grains smaller than 1 millimeter, the material ejected during the post-perihelion outburst. By analyzing its dispersion, researchers could measure how a passing interstellar comet can modify the environment of our own system. Astronomers also used this period to study the nucleus's reflectivity more accurately. The results confirmed 3I Atlas had a surprisingly reflective surface, with an albedo near 0.6, similar to some metallic asteroids. This property explained why it had resisted the sun's heat so well. Its surface acted like a natural mirror, reflecting most of the incident radiation back into space, a simple but effective survival mechanism. In the labs of NASA and ESA, scientists processed the last observations from the James Webb Space Telescope. The infrared spectra revealed that the nucleus's temperature continued to drop, eventually stabilizing around 183 degrees Celsius. At this point, all activity ceased. The comet had returned to its original state, a frozen, silent body journeying into the darkness, its brief, violent awakening now over. Thermal models showed that the cooling not only affected the surface, but also caused internal contractions. These changes could have resealed the fractures opened during perihelion, restoring the core's integrity. It was a process of cosmic healing, the comet mending itself after its encounter with the Sun. Astronomers were fascinated by the idea that it could continue its journey for millions more years. By mid-January 2026, telescopes recorded the last detectable images of 3I Atlas. Its brightness had dimmed to magnitude 18, far too faint for visual observation. On trajectory maps, a nearly straight line marked its final departure from the plane of the ecliptic. No human would ever see it again. However, its legacy would not be lost. The data stored in the archives would be studied for decades. For astronomers, the aftermath of 3I Atlas was the perfect ending to a story that combined resilience, transformation, and knowledge. It was confirmation that interstellar objects not only survive contact with stars, but also evolve through it. On its inbound journey, the comet arrived cold and inactive. On its departure, it left transformed, with a different surface and a chemical signature modified by our Sun. When it finally vanished from the telescopes, a sense of emptiness pervaded the observatories. The silence that remained was the natural echo of an event that lasted months. But it was also the beginning of a new era in astronomy, the certainty that sometime in the future another interstellar visitor will cross our sky, and thanks to 3I Atlas we will be ready. The passage of 3I Atlas marked a turning point in modern astronomy. It was not just another visitor, but a case study that redefined the limits of what was thought possible in cometary physics. The months of observation formed an unprecedented archive, a legacy that would change our understanding of interstellar objects and the evolution of the galaxy itself. The first aspect of this legacy was the confirmation of the chemical diversity of the cosmos. 3I Atlas revealed a composition dominated by carbon dioxide and complex organic compounds, with virtually no trace of water. This altered models of comet formation, proving that the universe does not follow a single chemical recipe. Each star system cooks its worlds in a different way, creating a vast array of planetary ingredients. The second fundamental contribution was the comet's structural resilience. Its dense nucleus and reflective hardened crust protected it from disintegration. For astrophysicists, this discovery demonstrated that time and cosmic radiation can transform a fragile body into an almost metallic structure, a kind of fossilized comet that has survived millennia of travel between the stars, a true veteran of the galactic wilderness. The third legacy was methodological. The coordinated observation between NASA, ESA, Webb, Hubble, Solar Orbiter, and dozens of ground-based observatories set a new standard for studying cosmic phenomena. This global, collaborative, data-sharing approach became the operational model for 21st century astronomy. 3I Atlas unintentionally became a blueprint for how humanity will study the unknown in the future. In the field of solar physics, the comet offered a unique opportunity to study the heliosphere from within. By tracking its interaction with the solar wind, scientists were able to map the Sun's magnetic field in a region where only theoretical models existed before. This information improved our understanding of solar activity and will help calibrate instruments on future missions to the inner solar system. The legacy of 3I Atlas also reached into prebiotic chemistry. The detection of complex organic molecules, the building blocks of life, suggests that the raw ingredients for life are not exclusive to our cosmic neighborhood. Astronomers now seriously consider the possibility that interstellar comets act as natural transport vehicles, seeding star systems with essential molecules as they pass through. Another important consequence was the advance in understanding cometary thermodynamics. The comet's delayed outbursts, driven by its internal thermal memory, led to a revision of classic models. Comets are now seen as dynamic systems with independent thermal layers capable of releasing energy gradually. The physics of comets, once based on local observations, had to be adapted to an interstellar scale. The technological experience also spurred improvements in early detection protocols. Automated search systems updated their algorithms to identify hyperbolic trajectories more quickly. Future visitors can now be studied even before they enter the inner system, allowing for the planning of intercept missions. The success of the 3I Atlas campaign became the catalyst for a new generation of interstellar exploration. In the wake of its passage, NASA and ESA announced plans for a joint mission called the Interstellar Probe Pathfinder, designed to intercept the next detected object and analyze it up close. Without 3I Atlas, this idea would have seemed premature. With it, it became inevitable. We are no longer isolated observers, but participants in a continuous exchange of matter between stars. Each interstellar visitor is a cosmic letter sent from an unknown location, written in the ink of elements forged in other suns. And while the light of 3I Atlas is no longer visible, its legacy continues to shine in laboratories and in the imagination of those who seek to understand the universe. It taught us that even the most ancient ice can turn into light when it finds a star.